Welcome to The Explainer. Today we are focusing on a concept we call the last samurai, mastering the paper. We are going to turn the Cambridge 9618 computer science exam into your personal, highly strategic battleground. Just like an ancient warrior mastering their blade, you need absolute precision to slice through these exam questions. Specifically, we're zeroing in on one of the most notoriously tricky, mark-dropping areas of the entire syllabus, justifying the use of data structures, stacks, queues, and linked lists. If you have ever stared blankly at a complex data structures question, your mind racing, wondering exactly what the examiner was to see, trust me, you are in the exact right place. We are going to break down exactly how to secure those top-tier marks using insider intelligence straight from the source material and the principal examiner reports. Let's get right into it.
So, let's start with the ultimate question. Why do so many students find applying data structure concepts to unfamiliar contexts so incredibly hard? To explain this, I want you to imagine two typical students sitting for this exam. We'll call them Alex and Sam. Now, Alex studies hard. Alex overloads their brain with raw computer science facts, memorizing every textbook definition of a stack or a queue, but offers zero critical analysis when writing the answer. On the other hand, we have Sam. Sam knows the material, but rushes. Sam sees a keyword, panics, completely misses the actual command word requirements in the prompt, and just word vomits everything they know. If you were to look at their papers side by side, it's just a sea of red pen marks from the examiner. Why? Because the difference between an average grade, like a B, and that coveted A star comes down to this single, crucial challenge. It's the hurdle of taking a rigid theoretical structure, whether it's a last-in first-out stack or a first-in first-out queue, and seamlessly adapting it to a completely new, unfamiliar, and frankly weird context that Cambridge throws at you on exam day. Examiners know this is the ultimate test of true understanding. Today, we are going to fix both Alex and Sam's mistakes and give you the absolute blueprint to conquer this paper.
Here is our strategic agenda for today's explainer. First, we'll tackle the unfamiliar context challenge. Second, we'll build the core theoretical principles. Third, we unlock the method mark strategy. Fourth, we'll navigate the top 3 examiner warnings. And finally, we'll master critical analysis and evaluation.
All right, Section 1, the unfamiliar context challenge. Let's talk about encoding the concepts.
Now this right here beautifully illustrates why rote memorization, like our student Alex was doing, just does not cut it. The assessment objectives for the Cambridge 9618 exam are strictly designed to target 3 very distinct cognitive domains. Notice how these domains act like a staircase. At the very bottom step, you have basic knowledge and understanding. This is knowing what a linked list is. But the marks quickly scale up as you climb into the second domain, application. This is where you actually use that structure in a specific scenario. And finally, at the very top of the stairs, the peak of the mountain is analysis, where you evaluate exactly why that specific structure is the absolute best choice. Just memorizing raw facts won't save you when the examiner asks you to climb all the way to the top and analyze a complex system. To get there, you need to decode the command words. Are they asking you to state, describe, or evaluate? Top students structure their answers using the PEL framework, point, evidence, explanation, link. You make your point about the data structure, provide evidence from the scenario, explain the technical mechanism, and link it back to the specific problem. It is a game changer.
To master these unfamiliar contexts and effectively use frameworks like PEL, the source material explicitly recommends a powerful memory hack using a visual story method. Instead of trying to painfully recall a dry paragraph of text during a highly stressful exam, you visualize the structure in the real world. Picture a massive teetering stack of heavy dinner plates in a restaurant kitchen. If you want a plate, you have to take the top one. The last in is the first out, LIFO. Now visualize a long line of people waiting outside a cinema in the freezing rain. The first person who got there is the first one let inside. First in, first out, FIFO for cues. This vivid visual encoding creates immense mental flexibility, allowing you to instantly map these structures onto whatever crazy context the examiner throws at you. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving right along to Section 2, Core Theoretical Principles, the architecture of a perfect answer.
Listen up, because we have a major examiner alert here. Principal examiner reports issue a massive, glaring warning that candidates consistently bleed easy marks because they confuse key terminology. Think back to our student Sam rushing through the paper. Sam might write something vague like, the data goes to the next piece of data.
Absolutely not. You will get 0 marks for that. It is absolutely vital to define your terms clearly before deploying them in your extended responses. You need to use precise words. Don't assume the examiner knows that you know what a pointer, a node, or null terminator is. State it clearly. Laying that initial solid groundwork proves your fundamental understanding before you start building those complex analytical arguments.
The theoretical architecture of a top-tier answer must rest securely on 3 foundational pillars. First, precise definitions, represented by the solid, standalone node graphic on the left. Second, clear relationships. Just like an interconnected network of nodes, you need to articulate the direct, causal links between structures. For example, you must explain exactly how adding a new element to a queue specifically affects both the head and the tail pointers. You can't just say it's added, you have to explain the mechanics. And third, integration. This means making active, intelligent connections to other areas of the computer science syllabus. When Alex and Sam finally learned to build their answers on these 3 pillars, it was incredible. We literally watched the red pen marks transform into green check marks. Building your answers this way signals to the examiner that you possess a comprehensive, structural mastery of the subject rather than just isolated fragments of knowledge.
All right, let's dive into Section 3, the method mark strategy. This is your procedural framework.
Now, you might not fully realize this, but Cambridge actually awards you marks for your algorithmic thinking process, rather than just the final correct answer. This is the method mark strategy, and it's how you salvage points even if you mess up the final calculation. When tackling an exam question, you must follow this exact step-by-step procedural framework. Look at the data on your paper right now. Let's do a 60-second visual scan in our heads. First, you deconstruct the question. What is the command word? Second, extract the relevant data, like deciphering the specific sequence of binary strings given in the prompt, maybe something like 01000 100 100, to interpret what the system is doing. Third, select your analytical framework. Fourth, execute your trace tables or calculations with clear, completely unambiguous notation. And finally, present your conclusion using the correct terminology. Showing your work isn't just a friendly suggestion from your teacher. It is literally how you accumulate method marks on the 9618 paper. Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
This methodological approach fundamentally proves your practical programming skills. The syllabus demands a continuous, unbroken cycle of algorithmic thinking. It requires breaking down the puzzle through step-by-step decomposition, carefully selecting the appropriate data structures, ensuring efficient code implementation, and outlining rigorous testing. Let's play Find the Flaw. If a student writes a paragraph saying they will use an array for a dynamically growing list of customer orders without explaining how they will handle the array running out of space, what's the flaw? The flaw is a total failure in decomposition and rigorous testing. By systematically evaluating the algorithmic performance at every single stage of this cycle, you are actively demonstrating the exact practical application skills the examiners are practically begging to see.
Moving into Section 4, this is crucial insider intelligence, the top 3 examiner warnings, avoiding the pitfalls.
Notice the stark contrast on this slide. On the left, we have a generic textbook definition of a linked list crossed out in harsh red. On the right, we have an explanation specific to an airplane booking system context, marked with a beautiful green check. Examiners are utterly ruthless about this. They explicitly report that answers must be highly specific to the context provided in the question. Let's do a 30-second speed writing exercise in your head. If the question is about a flight booking system and you write a flawless, perfectly memorized textbook definition of a linked list, but you completely fail to explain how the nodes represent passenger tickets or how pointers link sequential seat assignments, you will lose the majority of the marks. Context is king. You have to weave the scenario into your Peel paragraph.
Let's lay out the complete list of the top 3 examiner warnings, pulled directly from years of principal examiner reports. Number 1, confusing cause and effect within your data structures. Don't mix up what triggers an action, like popping an item off a stack, with the mathematical result of that action on the stack pointer. Be sequential. Number 2, forgetting to check boundary conditions and edge cases. What happens when the stack is entirely full and you try to push data? Stack overflow. What if the queue is empty and you try to dequeue? Underflow.
You must explicitly address these boundary conditions in your code explanations. And, number 3, as we just aggressively discussed, failing to anchor your answer specifically to the question's context. If you can avoid these 3 major pitfalls, you are already miles ahead of the vast majority of candidates sitting in that exam hall.
Finally, we reach Section 5, Critical Analysis and Evaluation. This is where we secure the A-star. To successfully evaluate algorithm quality, which is exactly what separates the top-tier A-star candidates from the rest of the pack, you must rigorously analyze these 3 specific quality metrics. First, time complexity. How fast is the execution speed of your chosen structure? Are you traversing an entire linked list to find one item, which takes time, or are you accessing an array index instantly? Second, space complexity. What is the memory footprint? Linked lists require extra memory for pointers. Arrays might waste memory if they are pre-allocated but empty. You have to discuss this trade-off. And third, edge cases. How do extreme conditions affect the overall performance of the system? When the exam asks you to evaluate or justify the use of a stack over a queue, your argument can't just be because it's better. Your argument needs to be firmly grounded in these specific analytical metrics.
Your problem-solving phase in these high-mark questions must utilize a rigorous deconstruct, solve, evaluate loop. Step 1. Identify the given information. Step 2. Break it into logical steps. Step 3. Solve the problem systematically. Step 4. Check your solution for reasonableness. Does this answer actually make sense in the real world? And Step 5. This is the absolute critical part. Make heavily justified recommendations. Higher-order command words demand that you evaluate alternatives and compare approaches. Again, you can't just state that a linked list is good. You have to justify exactly why it's better than an array for this specific dynamic data scenario, using time and space complexity as your evidence.
And this brings us to our ultimate secret weapon. I want you to read this quote directly from the Principal Examiner Reports. Principal Examiner Reports highlight that candidates referencing cross-topic connections achieve significantly higher marks. This right here is how you show true, undeniable mastery to the examiner. Don't treat data structures as an isolated island in your brain. Connect them. Connect the efficiency of a linked list to memory management topics. Connect the logic of a stack to how a processor handles subroutine calls in computer architecture. Integrating your knowledge across the entire Cambridge syllabus is what makes an examiner sit up, take notice, and confidently award you those top marks.
We have completely deconstructed the challenge, armed you with the Peel framework and the method mark strategy, and revealed the examiner's deepest secrets. This strategy is entirely in your hands now. How will you apply these critical tools to completely deconstruct and dominate your next unfamiliar algorithm? Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.